Alright, this lesson is about optimization. This is our third application of quadratics. So, optimization is just a really fancy word for making the most out of a certain restricted amount of materials. And so that's a real life situation that comes up in a lot of businesses and in a lot of real life situations. And a lot of times they involve quadratics. Not all the time. Sometimes they're more than quadratics or less, but specifically when we're optimizing something with area or volume, we'll end up with powers of x that yield either quadratics or cubics. So we of course won't do cubics, we're just going to optimize area today. And we're going to talk about sort of first how we write expressions for the side lengths with only the information about restrictions, right? So this will make more sense when we actually read this problem. So we're going to read this first problem. Josephine and her father are building a chicken enclosure in their backyard. They only have 20 feet of fencing to use and want to make it the biggest enclosure they can from it. So what we're focusing on here is that they only have 20 feet of fencing. That is our restriction. So we are going to use that restriction to write expressions for the side lengths of this enclosure. We know quite a bit about rectangles. First of all, that the perimeter of this rectangle needs to be 20 feet, right? We are going to use exactly 20 feet of fencing, but we can't use any more. So we know that the perimeter all the way around, all the way around around this enclosure is going to be 20 feet. So the first step in writing expressions for side lengths of optimization problems is just to label one side x, right? We have a lot of unknowns in this problem, but we're gonna stick with that's x, okay? And because we know about rectangles is that this side and this side are the same length in a rectangle. So if I've labeled this side x, this side will also be x. So see how we started by just labeling one side x, but now we can sort of lead on continuing with that the opposite side is also going to be x. There's a lot of ways to think about this. And we're trying to, it's early this morning and I have no words. Anyway, so we are trying to find an expression for this side length here. And it has to use x, because we can't have more than one unknown in our problem. So really all we have is that this side is x, these two sides are x, and that the maximum amount of fencing we can use is 20 feet. So what we can do is, like I said, there's a lot of different ways to think about this. In my brain, I'll show you what I do in my brain here. So what I think about is that this half of the rectangle is going to use 10 feet of fencing, right? Because it's a rectangle, so the opposite sides have to be the same. So if you take only two of those sides, a short side and a long side, then that's got to be 10 feet of fencing, so because the other side is going to be 10 feet. And if I've already used x feet of fencing, then what I have left is 10 feet minus that x that I used. So that's the way that I think about it. I'm also going to show you sort of an algebraic way to do it, because that is often helpful for people. And what we do for that is we label the other side y. So now we have two unknowns, and we're going to write an expression for the perimeter of this rectangle with our restriction. So I have two x's, I'm right over here, I have two x's and two y's, right? Add together make 20. That's just us adding all of the sides together and getting 20 as the perimeter. And then to sort of get to where we were before with the 10 minus x, we need to solve this equation for y. So we need a y equals something. So that will give us an expression for y using just x. And so you can do that many different ways. I'm just going to divide both sides by 2 because I'm noticing that's a common thread here. That gives me x plus y equals 10. And then to make it so that we have the y by itself, I'm going to just take away x on both sides. And we'll get, I ran out of room, we'll get y equals 10 minus x. So we now have this same expression that we got earlier for that long side of the rectangle. So the rectangle, no matter how we do it, it has one dimension that's x and one dimension that's 10 minus x feet. So these are our dimensions for our restricted rectangle, right? So we have 20 feet of fencing. One side we just labeled x, and you can either just think about it in like half of this is half of the rectangle is going to be 10 feet, and then do what's left after we already use x, which is 10 minus x. Or you can write this this expression for the perimeter of the rectangle using this other variable of y, and get the same expression. This method is really useful because it works even if you change the parameters, if you change the problem. So speaking of which, this next problem, Jared is building an aviary in his backyard. He has 16 feet of wall and ceiling materials available and wants to make the enclosure the biggest he can. To do that, he's going to use the side of his house as one of the sides of the enclosure. So we only are building 3 sides of this rectangle, not the 4th. And that's going to change our math a little bit. Is one of the set, but he needs to know the dimensions he should make the aviary. So we're not going all the way to what dimensions will give us the biggest enclosure yet. All we're doing right now is we're getting side lengths, expressions for the side lengths with those restrictions. The next page is the same problems again, but we're going to talk about optimizing that area. We're starting by getting expressions for side lengths. So the same process goes for this one. We're going to start by just labeling one side x, and I'm going to label the short side x here, and then I'm going to label this side y. And so I have 16 feet of wall and ceiling materials available. So 16 is our maximum amount of perimeter there, but it's not all the whole perimeter, it's just those 3 sides, because those are the only sides we're building, right? So I'm gonna again write an expression for the perimeter of this aviary. So I have 2 x's and only 1 y, and all of that has to add to be 16. And again, we need to have an expression that says y equals, because we need an expression for this length with just x in it. So I'm going to solve this by taking away 2x on both sides. Take away 2x. And we get an expression that says y equals 16 minus 2x. So we now have this expression that just has the unknown of x, that represents this side of the enclosure. So the dimensions for this will be x is one of the dimensions by 16 minus 2x is the other dimension. And those are our expressions for the side lengths of this aviary. I just put them in parentheses because it helps me see them separately, but it's not super necessary. So one side is x, the other side we figured out can be written as 16 minus 2x. Again, I just want to point out that that if you were to just think about this, if you label one side x, specifically the short side x, and then you know you have 16 feet of materials available, then that leftover side is going to be 16, which is the total amount. Take away the 2 x's that you used. So you can also think about it that way and get the same expression. For some people, the algebra is easier, and some people it's better to just think about this. You decide what's best for you. This last problem, we have something a little bit more complicated here. A pet rescue is trying to decide how to lay out their dog run and kennels. They have decided that they would like a square space on each side of the dog run in which to install kennels, and then a rectangular space between them for the dogs to be let out to play. They have enough materials for 400 feet of wall and are trying to maximize the area of the play space for the dogs. So here's our restriction, 400 feet of wall. And we have some ideas here. They're making each of these side spots squares. So they have to have the same side length on all sides. This, however, is a rectangle. And this is the important part because we are maximizing this area. And we'll talk more about why that's important later. But first we just need to have side lengths here. So what I'm going to do is I'm going to label this side X, and not this whole side, just this bit, right? And then we're going to go from there. So because I know that this side piece here is a square, I know that this is the same, and so are these. These two are both the same side length. So all of these have to be X. And because this is a rectangle, these two sides also match. So this has to be X. And likewise, all of the sides of that square have to be X as well. The only unknown here is this length right here. That could be anything. They have to be the same, but they could be anything. So our expression is going to look a little different. We have 400 feet of wall, but look how many x's and y's we have. So if we add all of those together, we have 1, 2, 3, 4, 5, 6, 7, 8 x's, 8 x's, and 2 y's. Have to equal 400 in total. And we're still trying to find an expression for this piece right here using our restriction. So we're going to solve this equation for y. So I'm going to take away 8x on both sides, and it will give me this expression, 2y equals 400 minus 8x. And then the last step will be to divide by 2, so that we have a y equals, running out of room here, y equals 400 over 2 is 200, and 8 over 2 is 4. So I get this expression of 200 minus 4x. So we have an expression for x, or these side lengths are x, and then y is 200 minus 4x. So I actually like to label these, once I've done the problem, I like to label them as what they are in terms of x. So I can see everything labeled in terms of x in my picture. Okay, so we've now figured out how to do the side lengths using restrictions, how to write expressions for side lengths using their restrictions that they're giving us. We're now going to optimize, and that's the part that takes our quadratics skills. So here is our same problem again. Josephine and her father are building a chicken enclosure in their backyard. They only have 20 feet of fencing, so you can look back at your other page, but I'm going to just label these side lengths x and 10 minus x. Those are my side lengths. What we're trying to optimize is the area of this chicken enclosure, right? So not the side lengths. We're not trying to make the side lengths the biggest they can be, but the area of this chicken enclosure. So we're going to write an expression for the area of this chicken enclosure. Area equals, and to find area, you have to multiply two sides of a rectangle. That's what, we already know that, right? So I'm going to just multiply my x by my 10 minus x. And I'm going to distribute this out and figure out what that looks like. That says 10x minus x squared. And it looks a little funny, but this is a quadratic right here because it has an x squared in it. That's a quadratic. So to solve this, to figure out what side lengths give us the biggest possible area, we are going to graph this quadratic. So I'm going to switch over to Desmos here. Just remember that, we're going to talk about that in a second, but just remember that you have your calculators and all other options to use for graphing this. So this is y equals 10x minus x squared. So we have this graph now. And this is a graph of the area of this chicken enclosure. This, I wish I could draw on this, but I cannot. So I will draw a picture. Actually, that's what I'll do. I'll draw a picture on our notes of this quadratic graph. I just want us to take note that the maximum here, the vertex, is at 525, and we'll talk about sort of what that means in a second. So we're going to switch back, and I'm going to draw this quadratic. It looks something like this. And this point up at the top was 525. And we're going to just talk about this axis right here, the x-axis. This is inputs here, right? That's our x values that we're inputting into this function. And x was one of the side lengths. So this is just basically the short side, or one of the side lengths. Very, just like we talked about last time with vertical motion, it's important to have context. Like our x values in this situation are one of the side lengths of our enclosure. So this is 5, right? Because we know that point is 525, we know that's 5. The y-axis is area. Because the side lengths depend on each other, right? We have one side length that's x, and then the other one is just 10 minus that value. We only need to know one of the side lengths to figure out the other side length, which then gives us the area. So what we're saying here is that the maximum area, which happens at this point, the maximum area happens at when we have one of those side lengths as 5, which let's just think about that really quick. So a chicken enclosure with one side length of 5 and the other side length of 10 minus 5, which is 5, gives us a square enclosure with the area of 25. So see how our input of 5 gave us an output of 25, because the input is one of the side lengths, the output is the area, which is good because we wanted to optimize area. So the optimal dimensions of this enclosure are 5 foot by 5 foot side lengths. And I'm also going to put that gives us an area of 25 square feet. So really all we're doing with optimizing is we're trying to find the vertex, and we're trying to interpret the vertex and what it means. So let's try this one. We have Jared is building his aviary, right? So we already decided that this side can be represented as x, and this will be 16 minus 2x. Those are our two side lengths. So again, we're going to write an expression for the area of this aviary, which is x times 16 minus 2x. Then we're going to just distribute so that we have a better idea of what this looks like. And this is a quadratic. That's what I'm going to stick in my calculator or a graph using my Desmos application in my case. So I'm going to replace this with 16 minus 2x squared. Oops, not 16, 16x. There you go. That's better. So we have this quadratic, and we're going to just take note that the highest point is 432. Again, I'm just going to draw a quick graph here. I maybe should have been a different color. Here we go. This point at the very top was 432. And again, remember that this is one of the side lengths, specifically the short side, right? The one that's connected to the house. And this here is the area. So our maximum, our optimal area is going to occur at 432. So a side length of 4 and an area of 32. So we're gonna just draw really quickly what that looks like. So on the, here's the house, and then we have a side length of 4. And let's figure out what the other side would be. So these two sides are 4, but what is this missing side? It's 16 minus 2x. So 16 minus 2 times 4 is 16 minus 8, which is 8. So this side length is 8, and that yields an area of 32. So you might, it's crazy to me, and I don't know why this I don't know. It's crazy to me that this is an optimal area, and so is this square. Like, you would think that if a square has the optimal area, then it would always be a square, but it's not. This is a rectangle. It's got a side length of 4 and another side length of 8. For some reason, not having to build one side of the rectangle makes it so that it's a rectangle instead of a square that gives us the optimal area. Interesting. So our answer to this question is the optimal side length would be 4 feet by 8 feet, which would give us an area of 32 feet squared. Fascinating stuff. I also wanted to show you, because I have this set up already, and why not? I created this when I taught this the first time. And I can just drag this to change the this is an aviary, I guess, in this case, that's connected to the house. Notice that when I'm moving it, it shows us the area there, but it also gives us this like parabola showing what the area looks like as we change the side lengths of the dog run. So a square, let's see, something like a square-ish, gives us more of like an area of 29, and optimally it's actually a rectangle with an area of, super close, 32, right? So super interesting stuff. So we're going to do this last problem, the one with a bunch of x's. Again, I'm going to label, this side was x, so was this, so was this, so was this. And we already figured out that this other side is 200 minus 4x. So important to note here is that we're not optimizing these areas, right? That's a square. That's gonna pretty much have the same area no matter what, right? But we are optimizing this middle area. We want to make sure the dogs have enough room to play. So what we're optimizing is the middle area there. So our function here is going to be the area of that middle dog run area only. So like x times 200 minus 4x, which gives us 200x minus 4x squared. So I'm going to plug that in super quick. Nope, we need, so y equals 200x minus 4x squared. Very tall quadratic. Let me just stretch this out a little bit so we can see better. So notice that our maximum point is at 2500. So I'm going to go back here and just draw a really quick graph. It's going to be much smaller than it is in real life. It's fine though. And the maximum point here is at 2500. So meaning this is 25 and the area is 2500. Again, the x-axis here is representing this side length of all of the squares, the squares that the kennels are going into, and also the short side of this rectangle. So the optimal, the side length that will give us the optimal area is 25 for x, for the x value. And the area that it's going to yield is 2500. So I'm gonna, before we write our answer here, I'm gonna just show you, I also have like this graphed, if I can find it. Here it is. Okay, so here's our dog run, right? As we move this, and both sides stay squares, it ends up looking like this, right? We can have teeny tiny squares and a very long rectangular dog run. And as the squares get bigger, the rectangle switches to being more vertical than it is horizontal. And watch the area move as I move this side length. The optimal area happens about here at like specifically 20, I don't know if I can get it to be exact. Oh, there you go. Exactly 25. And it's telling us the area is at 1250, but I think that's with different restrictions. So, so our problem is a little bit different than this, but I just wanted you to sort of visualize what is sort of happening here with the area of the dog run in the middle. So our optimal side length is for the short side to be 25, and we need to figure out what the long side would be with our restrictions. So optimal dog run would be 25 feet by, and the other side, if we plug in 25 to this, 200 minus 4x, let me do that really quick, 200 minus 4 times 25, that's 200 minus 100, which equals 100. So the other side of our dog run specifically is going to be 100 feet, which we can also tell because the area is 2,500. So we just, what times 25 makes 2,500? Well, 100, right? So 25 feet by 100 feet gives us an area of 2,500 square feet. And that's the optimal area possible in this specific situation with the restrictions, right? So again, what we're doing is optimizing with certain restrictions. If there were no restrictions, there would be no optimization, right? Because we would just make it as big as we wanted, which is infinitely big if you wanted it to be the largest area. So you need that restriction, that's important. Yes, but so the first part we did, just a quick review, is to make expressions for the side lengths. So labeling one side x is the first step, and figuring out an expression for the other sides using x If you want to use algebra, you can use algebra. If you want to think about it, you can think about it. And then you get an expression for the area by multiplying the two side lengths expressions, which gives us a quadratic, which we can then graph and find the vertex, or the maximum, which yields the optimal side length of the enclosure or the shape or whatnot. We are not going to do this extension problem. This is like a surface area minimizing problem. But you won't see something like this in your homework, so we're going to just leave that be. So let me know if you have any questions.